Okay, fantastic. So thank you, Fiodar and Deepak, for that excellent talk. As we're waiting for questions to come in, I wanted to ask one of my own questions. So I was curious, does it make sense to change the design of existing systems so that they're actually more amenable to POP? For example, rather than using the splitting algorithm, could it make sense to instead actually make systems themselves more granular, and to maybe refactor, redesign systems so they are granular?
Yeah, I think that's a good question. I'm not sure it's possible in all cases to design systems to be granular by default. I think in some cases you might have really large clients and there's no real way to get around that. But yeah, maybe it is an interesting idea to also think about how you can get systems granular by default. I'm not sure it's always going to be possible to do that, but yeah, it is an interesting idea.
All right, it looks like we have a live question from Max. So Max, could you please introduce yourself and ask your question?
Hey, thank you. Great talk. My name is Max. I'm working for a company called Astronomer now. I have a question related to how feasible the partitioning is, assuming if you have a lot of heterogeneous resources, is it always possible to break down this big pool of resources into equal, K-size subpools so that you can do this granular allocation?
Yeah, that's a great question. Yeah, if you have like a large amount of heterogeneity and you don't have that many resources of each type, you may break the granularity condition of like client resource fungibility. So we do propose this idea of resource splitting in the paper, where you can still, even if you don't have that many, if you have many unique resources, you can still kind of break up those large resources into virtual resources and then assign those virtual resources to each subproblem. So this is what we did for traffic engineering, for example, where you can consider every link between two sites as a completely unique resource. And in that case, there's actually only just one resource at every type. And so you can think of that as the most extreme version of what you considered. And the technique like still works fine. I would need to think whether in the case where you have many heterogeneous servers, for example, whether resource splitting is still a good idea. But yeah, it is possible that we could use resource splitting to transform an initially non-granular problem into a granular one.
And thank you. And piggybacking on this question quickly, so you're mentioning virtual resources. Do you think it's something that maybe some sort of abstraction or declarative language for physical resources could be helpful, or totally useless?
Yeah, I think it's an interesting idea. I would need to think about it a bit more, but yeah, it could be useful to as an abstraction to think about resources.
Thank you.
Yeah.
Great. So we also have a live question from Rohan. So Rohan, could you please introduce yourself and ask your question?
Hi, I'm Rohan from UT Austin. So you mentioned that problems like those in C2 and C3 can be converted to granular problems for applying POP to them. I was wondering, like, fundamentally, are there problems which cannot be converted into granular problems in POP?
Yeah,
Hello?
there are definitely problems that are initially not granular and you can't transform them into POP. Yeah, you can think of, for example, we have an example of this in the paper, but we considered like a facility location problem. And in certain formulations of that problem, you can't actually, you have this property where resources are not fungible, but also specific properties of the problem prevent you from being able to split those really special resources into smaller virtual resources. And in those cases, you can't actually use resource splitting to make the problem granular, and so you can't really apply POP, at least as we currently formulated it. One thing I want to note is that our paper focuses on randomly partitioning both clients and resources into subproblems and seeing if using simple partitioning techniques can actually give you large speedups with little drop in allocation quality. You can think of coming up with more sophisticated partitioning algorithms. That wasn't the object of our work, but it is interesting future work. And if you do use smarter partitioning algorithms, perhaps the space of problems you can apply something like POP to expands as well. Yeah, good question.
Thank you. Thanks.
Great. I'm going to switch my attention to Slack for just a moment. So Andrew Quinn at UIUC is asking if you could speak more about how you make non-granular allocations into granular ones. And he is particularly interested in scenarios where you want some affinity across client allocations to improve locality.
Yeah, great. Maybe Fiodar, you want to take this one?
Yeah, sure. Hey, Andrew, good question. So regarding how we turn non-granular allocations into granular ones, well, that's just, splitting up those big clients or rare resources so that we can actually partition them and have representations of them each subproblem. But I think your main point was about modeling affinity between clients, and that's much harder to do, right? So it's not guaranteed that if you have, say 2 jobs that need to be on the same rack or the same server in your allocation problem, if you partition your problem randomly, those 2 might appear different subproblems, and then you're out of luck. You can't actually get an allocation that works. That could be solved with something like a smarter partitioning that Deepak mentioned, right? First, taking into account affinity, and then partitioning while ensuring that clients that have affinity are within the same problem, so that doesn't become an issue for them.
Great. That sounds like an interesting direction for future work. So we also have a live question from Chirag. Chirag, could you please introduce yourself and ask your question?
Yeah, hi, I'm Chirag from UIUC. The question, so Deepak, since this work as well as Gabble was about heterogeneous, GPUs involved. So this is more of a question from a system side, and in the sense that if you were to implement something like a POP on a heterogeneous cluster, there would be significant overhead in breaking the resources, and because, for example, GPU is a coarse-grained resource as of today. Breaking down in terms of time or even in terms of memory, etc., incurs a lot of system overhead, and which is also variable because if you're sharing across jobs, etc. So how do you incorporate those kind of variables into something like POP?
Yeah, so in Gabble and in POP, we consider GPUs to largely be indivisible. So the finest grain of resource that you can get is like 1 GPU. So I think this is broadly true when we also support optional optimizations like space sharing, but we don't do anything super interesting when we do that. We are not allocating each resources within a GPU at some finer grain granularity, right? We're still saying, okay, 2 jobs can be given 1 GPU, but we depend on things like CUDA's multiprocess service to actually divide resources between those two jobs. But yeah, so and I think one other thing that I want to point out is that with Gabble, the allocation you're actually computing is some theoretical mapping of clients, which are jobs in this case, to resources, which are different types of GPUs. Mm-hmm. But then there's like another part of the system that actually determines how do you take this theoretical allocation and actually translate it to scheduling decisions where where jobs are given resources for a particular account. But yeah, so essentially POP is not concerned with that scheduling mechanism. It's really just trying to accelerate the resource
So
allocation.
POP would be like a layer over Gavel, but Gavel will probably take care of the.
Yeah, exactly.
Okay.
Yeah.
Got it. Yeah, thank you.
Okay, so a quick correction, by the way, Andrew was from UCSC, not UIUC. My apologies on that. So I think that's all the time we have today for this session. Thank you to all the presenters for some really great talks, and thank you to the audience for some really interesting questions as well. So the next session after a short break will be on scale.
On Slack or raise your hand in Zoom, I'll be able to grade you to panelists so you can come here and ask questions. Just to start off the session and questions here, Fiodar, so what class of problems cannot be mapped to granular? Are there a defined, very well-defined class of problems that cannot be mapped to it, or is it based on the constraints?
So I would say that any problem that we can't make to fit the definition that we described. So say the problem doesn't have that many variables. Well, we might not want to pop it anyway because it's fast enough to solve. Some problems might also have resources that we can't split using transformations, in which case, if those resources are few, then we don't meet the fungibility condition or the scale condition either. And POP doesn't work very well. There are some properties, problems like the facility location problem, where you're trying to, put, say, warehouses on a map such to satisfy a bunch of demands, some geographically distributed demands. Those can't really be popped either, because the resources aren't even defined ahead of time, so we don't even know what to split up.
Okay. So just going back to the talk from Facebook, the last talk we heard, there some of the jobs had 1 hour reservation time, so they can wait until the allocation is done. So if you assume that time is not a constraint or a knob, can you change the POP algorithm to run on non-granular full formulation of the problem when there is enough time, and fall back onto POP when you don't have enough time to compute? So have you thought about the trade-off being more dynamic rather than static?
I think what you described is basically, if time is a concern, then we might want to partition it. We might have to partition it. If time isn't a concern, then there's no need to partition. We can just solve the problem straight up. Now, what could happen is that occasionally the time becomes more of an issue, right? Say there's like a hardware failure and we need to quickly react to it. Well, we can't wait for an hour for the reservation to be computed. Maybe we want something in 10 seconds, right? So we're okay with a POP solution that might have a slightly lower quality because it's fast.
Okay. I was just wondering whether POP itself, is it easy to just change the POP algorithm to take a time as an input to pick the right one, make that decision dynamically rather than leaving it to the user, and then pick the right algorithm?
It's a little tricky because you'll get a rough estimate given the number of partitions, how long it'll take for you to solve, but the specifics can depend on the input, right? It might take 10 seconds, it might take 20 or 30. Right, so we give a rough estimate of how long it'll take, given the number of variables in each subproblem. But overall, there's no real guarantee that it'll finish within some SLO, for example. So you can get close, but it's not going to be exact.
Okay. Yeah, and you did talk about some experiments there. Is POP deployed in production somewhere, or is it based on the workloads, just the traces of the workloads, and you've shown it can do as well as otherwise? Or
yeah, maybe Deepak, you want to take this one?
Yeah, I can take that. So POP is not currently deployed in production anywhere, but we did get real-world traces from a traffic engineering workload on a private wide area network. And so those experiments are in the paper, and we found that POP does really well on that real workload. But yeah, most of the evaluation is on collected traces, and we would love to deploy POP in a real workload. So if anyone watching this talk wants to try POP on your workload, Fiodar and I are happy to chat.
Okay. Also, is there any theoretical bounds when you break the problem into granular compared to the original problem in terms of the upper bounds on the error or on any of the utility functions that you can bound, right? So as a function of number of partitions.
Yeah, that would be nice. And actually, we do have a bit of statistical analysis on a sort of simplified resource allocation problem in the paper, where one of the parameters is the number of partitions. You can see how the likelihood, essentially, of getting a bad solution grows as you increase the number of the partitions. And we have different variables also reflected, like the number of different resource types, the number of clients in the system, all that goes into this like statistical bound that we computed. But in general, given a specific kind of partitioning of the system, we don't currently have a good way of guaranteeing some gap between a popped solution and an optimal solution. And I think that's a great direction for some future work.
Okay. So is there, you did talk about the bound in terms of number of partitions there. Is there any bound on the convergence time of the algorithm or finding on the utility itself based on, let's say, max min fairness, right? So bound on how much it would be, the upper bound on how worse it could be compared to the full-blown problem itself.
It's hard to say, right? Given a random allocation or random splitting of these clients, you can probably come up with some really bad partitioning, right? Where all of your, big heavy jobs went into the same small partition and got the same number of resources as the same number of really tiny jobs. And that'll really skew your fairness metric because those heavy jobs are competing for a lot of resources and your small ones really aren't. So you can kind of run analysis to get worst case performance like that, but it's not going to be useful. The nice thing about the granular problems is that they're so big that having this random partitioning pretty much guarantees that this thing won't happen, or a bad partitioning won't happen. If it does, you just randomly try partitioning again and rerun it, and it'll probably be better.
Oh, okay.
Yeah, and we found just to add to that, we found in practice for max min fairness objective, we actually ran full traces using the Gavel simulator, and we found that the end-to-end metric that you care about, which is average job completion time for a fairness policy, is basically unchanged using the POP policy compared to using the full Gavel unpartitioned policy. So we found in practice that even though we weren't able to prove exact results on the final quality of solution, we did see very strong empirical results.
Okay. And how does that change with the number of partitions? Did you change the number of partitions there to see how it affects that metric?
Yeah, that's a great question. So the basic intuition as to how the number of partitions affects POP's behavior is that as you increase the number of partitions, you would expect runtime to decrease. So essentially POP gets faster because each subproblem is smaller. But also we expect quality of the allocation to also decrease, simply because it's more likely that you have some skew between each subproblem and the full problem. So that's the relationship you see. So if you have a particular time bound within which you need to compute the allocation, you basically want to pick the smallest k that will allow you to compute allocations within that time bound. Because if you increase the number of subproblems further, your allocation quality may needlessly decrease.
Yeah. So how do user find the sweet spot, right? Obviously, I can break it down into partition where each partition has one resource on one extreme. On the other extreme is all resources are in just one partition, right? Obviously, both are bad, and there is a sweet spot somewhere in between. And it's a trade-off between, as you're saying, the utility function and the time. So how do anybody who uses POP, how to think about finding that sweet spot on defining the number of partitions?
Yeah, so the optimal number of subproblems is very problem dependent, objective dependent, also dependent on the input you give us. So we found one effective way of finding the right number of partitions is to basically try a bunch on some held out data. So for example, for the real world trace where we did experiments, we had traces for multiple days, and we just took data from a single day and tried out a bunch of partitions and found what was the right sweet spot for that particular type of data. And so we would expect that real deployments of POP you would also have to do something similar, where you might have to play around a little bit with, for your particular allocation, what is the typical decline in allocation quality that you see as you increase the number of partitions, and also what types of runtime improvements do you see, and what are you basically comfortable with? Yeah.
Okay. Thank you so much, Deepak and Fiodar. This ends our session. Let me thank all the audience and the speakers here for the questions and the talk. It's a great session. I enjoyed it. Thank you so much.